Try is the imperative word. Okay, so I first want to really thank the organizers for inviting us to give a talk about this, because this is the only reason that last night, just before midnight, the paper was submitted on the archive. So it is going to be online.
We want to invite you to talk about be different than
And yes, just give me a date, and then. Okay, and the second reason I'm happy to give this talk is because there are many people here who know much more about what I'll be talking about. So the whole point is that maybe if we all get to understand what we need to understand, we can actually do it. So let's see. Okay, so I only have 1 hour. I'll try to be fast on the introduction stuff. What is the model? We have two players, they don't trust each other, they want to do some secure computation. Okay, so many different things. What we want to do is create protocols where they cannot cheat. Okay, and when we look at this model, there are some basic cryptographic primitives on which everything else is based. So for example, we talk about bit commitment, we talk about oblivious transfer. The thing that I'll be talking about today is coin flipping. So it was defined by Blum in the early 80s, and it's a very simple protocol. You have two players, they can send messages back and forth, they want to flip a coin. They don't trust each other, who's gonna flip the coin, okay? So hopefully we'll know by the end who's gonna flip the coin. There are two versions of coin flipping when we talk about quantum coin flipping, so I just want to make the distinction. So in the strong coin flipping, we want Alice and Bob to do a protocol to communicate with each other. It says that at the end, there is a random bit that comes out of the protocol, okay? And how do we talk about cheating? We say that Alice cannot bias the coin neither towards 0 nor towards 1 with high probability, and the same for Bob, okay? So they cannot bias the coin neither for 0 nor for 1, any of them, okay? On the other hand, when we talk about weak coin flipping, then we already assign a value of the coin, which is what Alice wants and what Bob wants. So we know from the beginning that Alice wants a 0 and Bob wants a 1, okay? And in that case, what we want is to say that Alice cannot win with probability higher than 50% in the optimal case, and Bob cannot win with probability higher than 50%. On the other hand, they could decide that they want to lose. Okay, so in the weak coin, I only see that Alice cannot cheat towards 0, cannot bias the coin towards 0, which is towards her winning the coin, and Bob cannot bias the coin towards 1, which is his winning the coin. Okay, but they could decide, Alice could decide that, okay, I let Bob win, the outcome will be 1, and she can always do that. Okay, so this is the difference between strong coin flipping and weak coin flipping. The weak coin flipping is not that weak, in the sense that if you look at what was the canonical example of coin flipping, Alice and Bob get a divorce, who's going to get the car? You kind of know that they both want the car, so a weak coin flipping would be good enough to solve this problem, okay? For other situations, we do need random coins, though. Okay, so this is the difference between strong and weak coin flipping. What is possible? Can we do this primitive? So everything is possible if we assume computational assumptions, classically. So take your favorite one-way function or hard problem, factoring discrete log, so that we are in a quantum conference, and you can do these things perfectly, or almost perfectly, okay? What we'll be talking about here is information theoretic security. So we don't want to make an assumption about the power of Alice and Bob. Can we do something? So classically, you can do actually nothing. So no matter what protocol you can devise, one of the two players will always be able to cheat with probability 1, okay? So this comes from min-max theorem and von Neumann's things. So
that's true for both strong and weak.
Yes, both for strong, for weak, for basically any of these, for bit commitment, for oblivious transfer, for anything, for these things. None of these things are possible information theoretically, okay? And the question was, what about quantum protocols? If we allow Alice and Bob to communicate with quantum channels, is something possible, okay? So the first results were negative in the sense that they showed that the cheating probability cannot be half. So we cannot have perfect coin flipping, neither weak nor strong. These are results by Myers and Low and Chow in the mid-90s. Okay? But then people started looking at coin flipping more closely, And what the first paper in the beginning of, in actually 2000 by Dorit, Amnon, Ashma, Umesh, and Andy Yao showed that there is something that we can do which is impossible classically, which is that you can devise a protocol where none of the two players can cheat with probability more than 91%. And this is for the strong case. Okay? And then came more protocols. There was a 75% protocol by Ambenis the year after. And then in 2003, there was a very beautiful result that showed that no matter what you do, there is a lower bound. There is a lower bound that shows that the cheating cannot be less than 1 over square root 2. Actually, what they showed is that the product of the two cheating probabilities is always bigger than half, which if you make them equal, it means that you cannot have less than 1 over square root 2. Okay? And this is the point where Kitaev introduced this formalism of coin flippings through SDPs and SDP duality, which we will use as well in order to get the weak coin flipping protocol. So we'll get back to this. And then quite a few years later with André Seyou, we showed that actually this value is optimal. You can achieve this 1 over square root 1 over square root 2. For weak coin flipping, so Kitaev introduced this formalism of studying these protocols that we'll see, and Mochon in 2007 actually showed that it is possible. So it is possible to have an almost perfect weak coin flipping when you allow Alice and Bob to communicate with quantum messages. Okay? So this is one of the few things that we know how to do. We know how to do key distribution. We also know how to do weak coins. Okay?
Your paper with André used that, right?
Yes, so I will say it again. So the way to get an optimal strong coin flipping is to say that give me a black box of an almost optimal, almost perfect weak coin flipping. I can use it actually in a classical reduction and give you an optimal strong coin flipping protocol. Okay? So the magic here is the Mochon's magic. It's very simple to get this once you start from this. Okay. A posteriori, it's very simple to see that it is the case. Okay, so why should we care about this coin flipping? So, as I said, it's one of the few primitives that we know how to actually do. Okay? So, what I want to say is that there is life beyond QKD. So, usually when we talk about quantum crypto, we stop at QKD. There are other things that we can study and things that are possible. The other reason is that there are some really, really beautiful techniques that go into these things. These are the things that started by Kitaev. We'll go through, I'll try to give you as much an idea as possible about these techniques and how you relate all these different things together. On the other hand, we don't really understand these techniques. So there is this very nice formalism that it was used to prove this weak coin flipping. One of the questions is, can we understand it so that we can use it for other things as well? So this is what we'll try to do. Then, as Thomas said, we can use this coin flipping to do other things. So in 2009, we used it to get the optimal strong coin flipping. 2 years later, we also used it to get the optimal quantum bit commitment protocol. So both these things use weak coin flipping as a subroutine. This one in a classical way, this one in a quantum way, in some sense.
Wait, I thought that we knew that we couldn't do bit commitment.
Optimal. I didn't say perfect. So we do optimal bit commitment.
Okay.
The probability is 0.73914 something,
Right.
some root of a polynomial.
Thank you.
Yes, yes. So these guys have constant biases, right? Okay, and the other thing is that there is many people in foundations, but also from computer science, that we try to understand quantum mechanics coming from a point of view of information, right? How can we see quantum mechanics as a theory of information? And one question that I would like to understand is that why do we live in a world where you can do these primitives, which are quite simple, with these weird constants? I mean, why is it that the constant for strong coin flipping is 1 over square root 2? You can say the same question, why the CHSH is cos square pi over 8? Where do these things come from, and does they tell us anything about quantum mechanics? Okay, that's a very vague thing. Okay, so why am I here after 7 years from Mochon's result to explain Mochon's result? So Mochon's result appeared in 2007. It's not very constructive. As we'll see at the end of the talk, it's still not very constructive. But it's not very constructive, meaning that there is a proof of existence. It's not a probabilistic method. There is really a construction, but it's not like I can tell you, this is what Alice does in round 1, this is what Bob does in round 2, this is what Alice does in round 3. Okay?
You can't easily, or there's a principal reason why you can't? I mean, if you would say PhD student here for 2 years, write down the algorithm, would it be possible, or is there something where really need to guess?
So I don't know where you find your PhD students, but I cannot put mine for 2 years to do this.
Is the information there, or is there
the information is all there.
Okay.
There is no efficient way of constructing it. That's all I'm saying. Yes.
But
So you can read, you can look at the proof. It tells you how to find the protocol. Okay. But at some point, you need to find some matrices of large dimension. You know that they exist, so you have to try them out and see which one is good, and you can verify
so
them.
we might not be able to build it even with PhD students.
So yes. So we'll see. We'll see what we mean with this. The second thing is that it was long, it was very technical, and actually it was never submitted, never peer-reviewed, and when we had our result in 2009, the first question that everyone was asking, yes, but do you really think that the Mochon's result is correct? So it took us a few years, but now we can say that, okay, yes, we do believe that the result is correct. So we started working in 2010, a long time ago, and these were our goals. We had to verify the proof, we had to simplify the proof, we had to understand the proof, and find a simple protocol. So 4 years later to last night at 11:40, have we verified the proof? Yes. Have we simplified the proof? At least half. You know, it was 80, now it's 40, but there are main parts of the construction which are simplified. There are other parts that are similar to what Mochon was doing. It still needs to be simplified more. That's why I'm trying to, involve you into this. Do we understand the proof better than before? Have we found a simple protocol? We have absolutely no idea how to do it. So we're just starting, and we need more people to work on this.
Carlos is like our Grisha Perelman.
Say it again?
Carlos Mochon is like our Grisha Perelman.
Exactly.
Well, maybe the opposite, since
Yeah, since he went through.
instead of
Right,
disappearing and living in a shack.
Right, if Perelman went to work for D.E. Shaw.
Right. Yeah.
Oh yes. I forgot to say that the problem is that Mochon is doing finance or something, and he has stopped caring about this a long time ago. So that's kind of part of the problem as well. Okay, so what I want you to understand from the beginning to the end of the talk is the following. There is one way of talking about protocols, which is the usual way that we think about protocols. You have two players, you have some Hilbert spaces, and at every round of the protocol, someone does some quantum operation in his part of the space, then the other one does some operation on his part, they go on for a bunch of rounds, at the end they measure something and they get an outcome. Okay, this is just an interactive protocol. This is how we can define a coin flipping protocol. Okay? Now here's another way. Here is a plane, and here are some points on the plane. They have coordinates, 0, 1, 1, 0. They have some weights. The weights are always probability distributions. So I have these points, and what can I do with these points? I can move them. I took this point, I split it into two. I put some new coordinates and new weights. Then I can also take a point and I can move it upwards. I move it up. Then I can take the 2 points up, I merge them into one. I take another 2 points, I merge them, and I end up with a final point. What did I show you? I showed you the existence of a weak coin flipping protocol with bias 1 over square root 2, because if you make this equal to this, then you can take u to be 1 over square root 2. And not only that, I showed you a proof that this is the bias. So the whole point is to say that instead of trying to find the protocol and trying to find a way of analyzing the strategies and finding the cheating probabilities, there is another formalism which is very nice to start playing with. You have points, weights on the points, you move them around with some rules, and at the end you look at your final point and you say, these are my cheating probabilities. And as long as you follow the rules, this gives you the proof that this is the cheating probability, that there exists a weak coin flipping protocol exactly with the cheating probabilities. So you shouldn't understand what's happening here. The whole point of the talk is to go from this formalism into this formalism. Okay? And then I guess the second part is to show that there exists something of this form where this point is arbitrarily close to half-half. Okay? This will tell you that there exists a protocol where the cheating is almost non-existent. Okay? Okay, so how can we try to do this? This has absolutely nothing to do with that. Well, it's not trivial. So this is where the beauty of Kitaev's formalism comes into the picture. Here are some of the things that we're going to use. We're going to start with protocols and cheating strategies. We'll start talking about semi-definite programs and duality of semi-definite programs. Then we'll go to something that will need a lot of help. We'll go to infinite dimensional convex cones. Then we look at operator monotone functions. Then we'll start taking duals of cones, dual of duals of cones, dual of dual of dual. Okay, we'll only do it twice. Then we'll use some catalyst things. And at the very end, this will show the equivalence of the protocols and these point games. So the goal is to go through a little bit through all of this and try to give you the main ideas of what goes into these things. Okay? So as I said, these are some really amazing stuff. We don't understand them very well. We can tell you why it works. We can tell you some intuition why it works. But really, it's the point where we should start understanding why they work and how we can use them further. And the second part is to show that this is what monotone did, that there exist this point game, these point things that go to this point half plus epsilon, half plus epsilon. Okay? This will conclude the proof.
Is it known that you can't do weak coin flipping with epsilon equals 0?
Yes, this goes back to Myers and Lo Chow.
All right, good.
Yeah. And one thing we will try to study as well is what are the resources we need for this epsilon?
Yep.
How do the resources of the protocol scale? Sorry?
There is one lower bound.
Yes, so there is a lower bound on the number of rounds. So what we know is log 1 over epsilon. So if you see our rounds, you'll see the difference between the rounds we need and the log 1 over epsilon. Okay. So here is how the proof will go. So we'll start with defining the protocols and writing them down as SDPs and dual SDPs. Okay? This is the first part. The second part is to try to define some point games with some rules on how to move these points on the plane. And these rules will have to do with matrices, with positive semi-definite matrices. Okay? Why? Because then we can relate it back to the SDPs. The SDPs will give us some matrices, will define how these points move around through these matrices. Okay? So we'll see exactly what this means. And then we'll end up with these point games where the rules have to do with matrices and semi-definite constraints, and we'll say still we don't know what to do with them. So we'll try to define a different type of point games, and to go from here to here is where we use this topology and the geometry of sets and cones. Okay? We end up with this, where the rules now of the point games will be very simple. It will say, I give you a function, verify that the sum of the values of the function on all points is 0, something like that, something that you know how to use. Okay? Then we'll do another step, and then we'll, there are many steps. So let me start before. So we start with trying to see why the protocol can be written, why the cheating probabilities of the protocol can be written down as a semi-definite program. Okay? So let me write down again the protocol. This is the protocol. We have 3 spaces. This is Alice, this is Bob, and this is the message space. We start with the all 0 state, and at every round, Alice does something on her workspace and the message space. Then this message goes to Bob, then Bob does something on his space, and so forth. What they do is just a unitary operation, and we have to add these projections, but for now, just forget about them. So at every point, they do a unitary. Okay? So the initial state is some state psi 0. The honest states, we define the honest states after each round to be psi I. We have these unitaries that either act on Alice and the message or Bob on the message. And what do we know about the outcome at the end? This is a honest protocol, which means that this is the projection that Alice outputs 0, and this is the projection that Bob outputs 0, and this probability is half. So the probability that in the honest protocol they they both agree that the output is 0 is the same as the probability they both agree that the outcome is 1, and it's half. Okay? So this is what defines a weak coin flipping protocol.
You say that you want exactly 1/2 in the honest case.
Yes.
Does this also hold for all the negative results? Because I would be okay with something which in the honest case has a very small bias. And so if you could get, for example, I don't know, a strong coin toss with negligible bias, but also in the honest case, that would be perfectly nice.
No, it depends on who you talk to, but I think the honest probabilities will appear in the lower bound in some sense. If you say that you wanted the honest case that this is 1, then there is a protocol,
Sure,
just output 1.
I mean,
so
in the classical results that I know, they also hold if you say the honest probabilities, so you have some relation between all the probabilities.
There is a relation
big.
between the honest probability that you put here and the bounds you get on the cheating.
Also in the context.
Yeah.
So it's not open.
Okay, so this is the protocol, and now what I want to say is that don't get scared, this is very simple. I write down an SDP that captures the cheating probability for Bob. Okay? So what do I do? What will Bob try to do? Bob will apply not the honest operations, but some other operations. And what is he trying to do is that at the end of the protocol, he's trying to maximize the probability that Alice will output 1, because 1 means that Bob wins. Okay? So what are our variables? Our variables are the states that Alice has during the protocol. Okay? What Bob is trying to maximize is the probability that when Alice will make her final measurement, she will get 1, which means that Bob is going to win. And there are some constraints about how these states can evolve during the protocol. So what are these constraints? The first one says that in the beginning is the state psi 0. And then it says that when Alice is moving, when it's the round that Alice is doing something, Alice is actually performing the correct honest unitaries, which means that the state evolves according to the honest unitaries U. Okay? And what happens when Bob is moving, then we don't know what Bob is doing. But what we know is that Bob does not act on this space, which means that if we look at Alice's part of the state, it remains the same. Okay? This only means that Bob's operation does not touch the part of Alice during the even rounds. Okay? So this is the SDP. I'm looking at states on Alice's side, says that at the end she measures 1 with high probability, and the states evolve according to the constraints of the protocol. Alice honestly applies the U's, and Bob applies whatever he wants, but he doesn't touch Alice's place.
Does this, where in this is it that the operations that Bob does are unitary and so on? Or don't we include that? I mean, I see
I
that
forgot. Okay, rho are quantum states, if you want. Okay, that positive.
Yeah, that should be, then there will be some operation.
Okay, so I can write the same thing for Alice. What is the problem is that if I try to find what is, okay, this is what I want to calculate, I have to go over all protocols. I don't know how to go over all protocols because this is a maximization thing. Okay? So what do I do when I want to go from maximization to minimization? Then I just look at the dual. Okay, so I'm not going to go precisely on how you go from the primal to the dual. This is just semi-definite programming quality. But what happens?
The maximum is not over all protocols. The first maximum is for a given protocol, you maximize over all things.
It's overall cheating strategies for Bob. It's not the protocol, it's the cheating strategy. You're right. Yes. So the thing is that if I want to find what is the maximum, I have to look at all possible cheating strategies for Bob, which meaning all these possible rows and I have to find the maximum one to say that the bias cannot be more than something.
Wait, sorry, isn't that like a small SDP? There's nothing, you don't need to go over larger and larger matrices, right? The row of Alice's are fixed size. They're defined the protocol.
Yeah.
So I don't understand. Is this a well-defined SDP, or you need to somehow go
but
over
this
larger?
doesn't search over protocols, right? I think this is what it said. First, you have to fix a protocol. Like
So what this tells you is that if you give me a protocol,
Yeah.
I can try to find the maximum cheating probability, which is I have to look over all possible matrices rho, which means over all possible cheating strategies for Bob, and then I will tell you what is the cheating probability for this specific protocol.
Which is some SDP. This is an SDP.
Yes, that's all we're saying. If you want to calculate the cheating probability for a given protocol, you can solve an SDP.
But you don't have an upper bound for Bob's size, right?
So your variables are Alice's part. So this is, as what he said, is that this is fixed from the protocol.
It's a very large SDP, right? Because you don't know.
Of course it's large, and of course you don't know how to solve it, yes. But, okay.
So,
So the U's are fixed from the get-go? Or
Yes, the U's are the protocol. The protocol tells you what are the U's.
And you also know how many rounds you're going?
Yes, you also know the rounds of the protocol. Yeah.
so just to clarify Or's question, I think what Iordanis meant is that for a fixed protocol, it is a simple SDP to find the
Yeah.
cheating strategy. But if you want to find a protocol with a good PB star, you have to minimize over all protocols.
Okay, so how do we define the dual? Well, okay, so what are the constraints? The constraints will be matrices now. Okay, for every constraint here you get, for every constraint here you get a variable. The variable will be matrices. The matrices will be positive. You get some constraint about how these matrices go from round to round. And what you know is that, again, for odd rounds, this relation has to do with these unitaries. For even rounds, these matrices, Z's, remain the same. And your initial condition here, that your initial state was psi 0, kind of translates to the fact that the last Z is the projection, the honest projection at the end of the protocol. Okay? And we add an extra constraint that doesn't going to change the value of this program, which is that we ask that the Z, the first ZA0, has actually this psi 0 as an eigenvector, okay, with eigenvalue beta.
Are you going to give us an interpretation of the Z's in terms of the protocol, or is it important? Or? The primal variable is it's clear, right?
Of course it's clear. So it's not obvious. The Z's, you should think of them as projections, but even that is not correct. Okay? And what they're trying to do is kind of capture how much cheating is going on during the protocol. So I think it will be a little clearer just in the next slide. Okay? Okay. Okay, so the first thing I want to say is that, okay, so let's try to understand what are these Z's, right? So what will be a solution to the dual? A solution to the dual will be a set of matrices Z, N for Alice and N for Bob. Okay, I forgot to say that there is one dual for Bob and one dual for Alice. So let's say we solve both these duals, we get the sets of matrices which are solutions. What do these things tell us? What they tell us is that they give us an upper bound on the cheating probabilities, right? So this dual feasible point, which is just these sets of matrices that satisfy the constraints of the dual program, is actually a witness of the security of the protocol, okay? Because if you see here, what we are saying is that PB is the minimum over all Z's of the projection of this psi 0 on this Z0, okay? So if I find any Z that satisfies these constraints, this will give me an upper bound on this cheating probability, okay? So this is better than the primal in the sense that if I want to prove that the protocol cannot cheat more than something, okay, I can solve the primal, or I can go to the dual, I can find a solution of the dual, and then I get an upper bound on this thing, okay? Okay, so what I will need to keep from this SDPs is that this matrix is Z's, okay? And what I care is how this psi 0 actually projects onto this, think of it as this observable Z, okay? Okay, and here is what is the problem with the dual? Why are we not happy with the dual? Because here, as Dorit said, this is for a specific protocol again. So if you give me a specific protocol, I can give you a bound on the cheating probability. What we really want now is to find the best protocol, so we have to go over all protocols. So that we don't know how to do. So we want to move away from these SDPs, okay? So what is the next thing is to go from these SDPs to these point games, okay? So how do we do that? So I showed you what is a point game. what is a point game is something that has some points with some weights, and they move around, and at the end they end up in one point. Okay? So let's try to give to start giving a definition of what the point game is. Okay?
Sorry, I missed this probably. What's EBM?
Oh, expressible by matrices. Oh, I didn't put it anywhere. Okay, because the thing is that we want to relate these point games with the SDPs. What we will relate it to is this dual feasible point, these matrices. So basically, we'll use the constraints that these matrices have from the dual to say something about how these points are going to move around. We'll associate to these probability distributions matrices, and we'll have constraints on these matrices. That's why, I mean, you'll see, that's why we call these games expressible by matrices. Okay? We'll see what...
But there are there are a subset of point games, or did you actually mean the same?
First of all, I mean, to this point, I haven't defined the point game. Right? Okay, if the point game is points on the distributions on points on the plane that they move around, yes, this is a point game. This will be a restriction of these point games. We want to put some rules on how these points can move around.
Sure.
Right?
Yeah.
So this is exactly what we want to say.
I just want to know if in my mind I could think of this as being point games, even though you haven't defined them yet. Or
oh yes, these are point games. This is this will be equivalent to the very end. Yes. So these are the point games we want to look at, okay? But we want to define them, okay? The point is that we want to define them in the way that they're equivalent to these dual feasible solutions, so that when I look at the point game, I will get a security witness about the cheating probability of the protocol, right? So somehow I need to relate these things. Okay, so let's start defining the things that we already know. So what is a point game? It's some distributions, P0, P1, Pn. Okay, they're distributions on points into D, into dimensions. This is what we've seen. And, you know, what we'll see is that, or let's take it for granted, we always start from a uniform superposition of the points 0, 1, uniform superposition, a uniform distribution of the points 0, 1, and 1, 0. This kind of corresponds to the fact that in the honest protocol, with half probability Alice wins, with half probability Bob wins. And the last point will be some beta alpha point, and we want this to be a witness about the cheating of the protocol. So we want beta to be an upper bound on the cheating of Bob, and alpha to be an upper bound of the cheating of Alice. Okay? And now we want to add more things so that this is actually true. Okay, so there are two questions that we should ask. First of all, what are these points and what are these weights? What do points represent? What are these weights? What do these weights represent? And the second thing is that how can we go from one distribution to the next one? Okay? So I should tell you what do these things represent, okay? And what are the rules to go from one distribution to the next? Okay, so as I said, the points and the weights will come from these dual feasible points and the honest state of the protocols. Okay? So what is the dual feasible points? Is these matrices Z's that satisfy the constraints of the dual SDP. And what do we know? We know that if I take the projection of psi 0 on Z0, then this is an upper bound on PB, and the same with ZB is an upper bound on PA. Okay? So kind of what we really want to look at is the projection of the states, of the honest states, when we try to measure them with these observable Z's. Okay? So really what we're going to look at is this quantity. And this is, you know, this is exactly the quantity that Kitaev used for the strong coin flipping lower bound. Maybe Zef will have something to say about why this is what we want to look at and how it relates to other things. But the idea is that what we are looking at is how the honest states are projected when we kind of try to measure them with these Z's. Okay? And what we need to make sure is that we look at the cheating probabilities together. If I just look at one cheating probability, I can always find the protocol that has this cheating probability equals to half. The other one will be 1. So somehow we need to take care of these cheating probabilities at the same time. Okay? So the way we do it is that instead of looking at Z, identity, identity, and identity, identity, Z, we're looking at this operator here, which is Z, identity, Z. Okay? So we put the two Z's together. So why is this a good thing to do? Because if you look at the initial state, psi 0, then psi 0 is a separable state. So this thing is actually an upper bound on the product of the two things. Okay? So this thing here for psi 0 is the product of this times this. Okay? So somehow it makes sense that this is what we want to keep track on. At the end, this will tell us something about the product of the two cheating probabilities. Okay? However, this product structure is not true for general psi i's because these are not separable anymore. But okay. So this is the quantity that we're trying to represent in these points on the plane. And how do we do it? Well, the points are just pairs of eigenvalues. So this is a positive matrix. This is also a positive matrix. Let's look at the eigenvalues of these things. So ZAI are the eigenvalues of this. ZB are the eigenvalues of this. So the points on our plane are just one eigenvalue of the first one and one eigenvalue of the second one. Okay? And how are we going to keep track of this quantity? The weight that we're going to put on this point is basically the projection of the honest state I on the corresponding eigenspaces. So there is an eigenspace that corresponds to the eigenvalue ZAI. This is the projection onto this eigenspace. So what I'm putting as points are pairs of eigenvalues of these two matrices. And what the weights are just the projections of the honest states onto the corresponding eigenspaces. So somehow, I need to keep track of these z's. And what I'm saying is that the only important thing about these z's is basically their eigenvalues and how the honest states project onto the eigenspaces. I don't really care what the eigenspaces look like, or what they are, or where they are. What I care is that what are the eigenvalues and what is the projection into the corresponding eigenspaces. Okay? So now you know what are the points and what are the weights. Yeah?
Can we think of this geometric quantity as some kind of a potential function throughout your protocol?
Yeah. So what you say is that in the beginning, you know that this is equal or it give you something like that. For n, you will know something because the Zn's are the honest projections of the protocol. And you want to see how this moves from round to round. So the idea is that in the beginning, this starts with the points 0, 1, and 1, 0. What Bob is trying to do is move it towards a point where his coordinate is high, which means that he can cheat a lot. But what we'll try to see is that if we pick these z's correctly, then you can always move this point closely to half and half. Okay? But yes, it is a function that we know what happens in the beginning, we know what happens at the end, and we know how it moves because of the constraints of the semi-definite program. This is what will happen. Okay? All right, so I'm very late, but at least I hope you understand what are the points of these point games, pairs of eigenvalues, what are their weights. Take the honest states and project them onto the eigenspaces. And now what I need to tell you is how can I move from this distribution to this distribution. And this basically will come from the fact that I have these constraints on these z's. Okay? So for example, at every round, only Alice is applying the operation, or only Bob is applying an operation. What this means, if you look at the constraints of the dual, is that from the I-1 round to the I round, one of the two Z matrices, either for Alice or Bob, is the same. What does this mean? It means that the eigenvalues remain the same, which means that the points cannot move anywhere, but they can only move either horizontally when one is moving, or vertically when the other one is moving. So I cannot take 2 points and move both coordinates at the same time. This comes from the fact that either Alice applies an operation or Bob applies an operation. Okay? So every time I move to a different distribution, it's like a round in the protocol. One player applies something, so I know that the points will move either horizontally or vertically. Okay? So that's already there's something about what kind of transitions we can have. And the second thing comes from the fact that I need these matrices to satisfy this constraint, which is just the constraint of the dual. I will see how to express these constraints in a sense that it will be equivalent to this thing. This is what the goal is. Okay, so now I can actually define what are EBM games. They're distributions. I start with this, I end up with this. I can only move horizontally or vertically. And this is the constraint that I add. So let's try to parse it. This is, I think, the hardest part of the talk. But okay, so what does this mean? What kind of distributions do I allow? I allow distributions on points. Okay, I look at its line. So here I talk about 2 coordinates. but as I said, points will only move one coordinate. So I can fix one coordinate to be always something. I only look at one coordinate and how it moves. So what it says is that the weights I can assign into these points x must come from some matrix x, okay? And the weight, the points correspond to the eigenvalues of this matrix, and the weights correspond to the projection of substate psi onto the corresponding eigenspace, okay? How did I come up with this? This is exactly what I was saying that comes from the z's and the dual, right? So what I'm saying is that the only distributions I allow are distributions for which the points are eigenvalues of some positive matrix, and the weights are the projection of some vector psi onto the corresponding eigenspaces, okay? I do the same for pi plus 1, because each distribution is like that. So there are two matrices, x and y. And the extra thing is that x must be smaller than y, okay? In the positive semi-definite way. Why should this be the case? If you, roughly these x and y's are the z's, and this constraint is exactly the same as this constraint, okay? One needs to prove it, but I'm not going to prove this part. But the reason we defined it like them is because they come from these matrices z's. The constraint that x is less than y is exactly the constraint that comes from the dual SDP. Okay? So, with this definition, what have we shown? Basically, we have shown that these kind of games, where I have points that move, but they move in this specific way, are equivalent to having a protocol and a dual feasible point, meaning a security guarantee for the cheating of the protocol. So this is off the 1 hour, right? Because go on. No, I'm kidding. I'm kidding.
Thomas, go ahead.
Just at some point, and maybe this is where it's happening, there's something where the protocol is disappearing. So when you wrote down the dual,
no, the protocol is kind of still here.
Okay.
Going from x to y means some u.
It's this.
But what about E? Wasn't E something? Oh, and U
E is a projection. Just forget about them for now. Just
okay.
This is a U.
Okay, so U is something that.
The protocol is the U's, right?
Okay.
The protocol is defining the unitaries that Alice and Bob do.
Okay, so on the next slide you didn't write any U, right?
Here there is no U, but here, yes, X and Y are not Zi and Z minus 1. It's Zi and Zi minus 1 conjugated by the U's. Okay?
No, because I'm just for the big picture, you had a protocol, and from the protocol you defined a dual, and there were dual variables, and then you're telling us what you really want is to find the protocol. So, you know, at some point the protocol disappears, and you're sort of searching for it. I mean,
Transition from x to y.
If I give you X and Y, you can find the Z's, okay? You can also find the U's, because the U's is just the change of basis that takes the eigenbasis of X to the eigenbasis of Y.
so now you're saying you're defining allowed transformations on these dual variables, such as if you follow these allowed transformations, then there actually always exists a protocol for which these new Z's are.
And this is the part which is not constructive. This is exactly the part which is not constructive. This says that if I give you a protocol, if I give you a game like this that follows these rules, okay, if I also give you the matrices X and Y and psi that verify that this thing is actually a good game expressible by matrices, then there is an efficient way of getting the Z's, which means the security guarantee, and the U's, which means the protocol. Okay? However, what this says is that there exist X, Y, and psi says that this is true. Okay? At this point, and this is the problem with this thing, is that the only way we know on how to find an EBM transition or try to verify it is to try to do a brute force thing of looking at the matrices and seeing if they exist and satisfy this constraint.
It's not even an SDP or something? You say brute force?
Is there an SDP to find the matrices?
You haven't defined the way combinatorially.
No.
So
I'm not
that's
sure.
what's missing.
I would say no, but okay. No, no, then it would be efficient. Okay, it could be a large SDP. Okay, so the point is that I defined the game like this precisely because I want it to be equivalent to this dual feasible points, right, and the protocols. And I tried in high level to convince you why this definition is equivalent, because this x and y is as roughly your z's, and this u's is just, you can also find the u from this x and y. So once you know a game like this, you are able to construct a protocol, but not only a protocol, also the dual feasible point that will tell you what is the cheating of the protocol.
Just to make sure, you don't even know the dimensions of x and y, right? You have no limitation.
Okay, I'm skipping many things. You do have bounds about what this x and y should look like. Okay, I mean, I haven't put everything, but yes. Okay, so we are done with this part of the proof. As you see, there is a lot to go. So what I try to convince you is that there is a way of going from duals to these point games, but these point games that are still not very easy to use. These point games that have to do with these matrices. Okay, so now what is the next part of the proof is to find an equivalent characterization of these matrix constraints. Okay, and this is the point where we use this geometry and these cones. Okay, so this is the part that is quite different from what Mochon did. No, in the following sense, he does use operator monotone functions, he does define valid functions, but these things are not defined as dual of something or the dual of something. And when he tries to prove it, he kind of has in mind that there should be an easy geometric proof that should work, but he says, I don't know how to do it, so here is 20 pages of integrals and perturbation theory. So this is the part of the proof that has gone out, and I will try to give you the simple argument that should work and how we actually make it work. Okay? Because it's very simple and obviously doesn't work, but you tweak it and it works. Okay, so the first thing is that I was talking about probability distributions that one goes to the next one, to the next one, to the next one. So forget about these transitions, let's talk about functions. So what is the function? Just take the difference of one with the previous one. Okay? So if I had a transition between distribution P0 to P1, let's think of a function P1 minus P0. Okay? So whenever I give you transitions, you can look at functions. Whenever I give you a function, then you can look at the positive part of the function, the negative part of the function, and this will be an EBM transition. If this is an EBM function, then this will be an EBM transition. So you can go back and forth between these transitions, EBM transitions, and these EBM functions. Okay? Why do we do that? Because functions we can actually work with.
So these are formally discrete probability distributions of the
So these functions are from 0 to infinity to R, and they have finite support. So yes, so let's define something more rigorously. What is our space? Our space is the set of functions from 0 infinity to R. They have finite support. This is an infinite dimensional vector space. There is the L1 norm, and the basis will be just the Kronecker basis. Okay? Not important. The argument is still simple. The argument is said, let's look at the set of these EBM functions. Okay? We can prove that it's a convex cone. Very good news. It's not closed. Not so good news. It's infinite dimensional. We saw things that happen in infinite dimension. So, but what is the idea? The idea is very simple. I have a set, and I want to find a different characterization of the set. So what do? I look at the bidual. I look at the dual of the set, and then I look at the dual of the dual. And this will tell me something about the set I started with. Okay? This is the whole part of this proof. Once you understand this, then you're done. Okay? You need to prove it, but here is the idea. This is the set K. We started with these weird functions, EBM functions. The miracle that happens is that if you look at the dual, this is something that is very well studied. And the dual of this set is just the operator monotone functions. What is an operator monotone function? It preserves the... If for two matrices x is less than y, then f of x is less than f of y. Okay? So it's monotonic when... Say it again?
What's the definition of EBM function?
EBM function is just a function where if you take this, it will be an EBM transition. An EBM transition is just what I defined. Okay? So there's nothing between a function and transition. Think of them. This is exactly what I defined before. It's the things that come from this, the distributions on points that come from these matrices, okay, with these constraints. Now, I don't want to deal about matrices, so what I do is that I take this set of EBM functions, these are with finite support, and I look at the dual. And what I can prove is that the dual is isomorphic to the set of operator monotone functions, okay? There are two really cool stuff about this. The first is that we know which are the operator monotone functions. There are not that many. You can have the constant function, you can have the linear function, you can have one more, a little more weird function, but we know these things, okay? So what does this mean? It means that if I look at the dual of the operator monotone functions, and I call it the set of valid functions, okay? I'll just give it a name. Then a function is valid if and only if, for any operator monotone function, this simple condition holds, okay? Take the function h, just sum up all the values of h of x times f of x, and if this thing is always non-negative for all operator monotone functions, then this function h is in the set k star star. Okay? This is just the definition of duality. I had the cone, I took the dual of the cone, this is just the duality
Summation over what?
over the points in the support of h.
Which have finite support.
Yes, which has finite support. That's why it's a sum. Yes, sorry. So yes, this x is in the support of h. Okay? So what does this mean though? I know what this f look like, so I can equivalently write down this condition as something very simple. A function in h is valid if these three conditions hold. If you sum up the x's on their support, then it gives you 0. If you sum the xh of x, then it's positive. And for every lambda, this guy has to be positive. Okay? So what did we do? We started with a set of functions that you had to find some matrices and some vectors that satisfy some constraints, and we had no idea how to do anything with them. And we said that basically, if you look at the bidual of this thing, it's something which is very easy to describe. There are functions with finite support that satisfy these three constraints.
Yeah, but we should probably say that this characterization gives you the extremal rays of the dual cone, and therefore it's so easy, right? But here, this characterization theorem for operator monotone functions is exactly the extremal rays of the dual cone.
It's exactly
The extremal rays.
The extremal ray. Yes. So,
right? And these lines which...
So, what I showed is that this k star star has a very nice structure. I didn't show that k star star is actually k. And this is not true. So k star star is basically the closure of k. Okay? Because you need to take, okay? This is what duality, the bidual is the closure of the initial set. Okay? So these valid functions are very nice. They're equivalent to the EBM functions up to this closure problem, but intuitively they should be EBM functions or they should be approximated by EBM functions. Okay? This is the main idea. Okay, so maybe I skip this part. Jamie will give you more examples of point games. I'm just saying that there is simple to see some transitions that are valid because all we have to satisfy is these things. So for example, you can move a point into 2 points. You know exactly what the weights and the points have to be because you have this inequality. You can raise something, you know when you can raise and all these things. So this was the whole point, that we go to a point game where you can see that it's valid. Okay? What I haven't showed you is exactly how to conclude this argument that this k and k star star are roughly the same thing. So if k was closed, then we will be done because the closure of k is k, so valid functions will be exactly EBM functions, but we are not closed. Even if we're not closed, if we're in finite dimensions, still would be fine because what we can define is basically the interior of k star star and the interior of k. And if these things are convex, which they are, if I have two sets where one is the closure of the other, if I take the interior of both things, then they're equal. Okay? So this is the interior which we call strictly valid, where the difference is that we put a strict bigger than 0 instead of bigger or equal. This you can show that in finite dimensions is the interiors are the same, and the interior is inside K. So what we showed here is that this slight subset of, okay, I'm not saying anything. What we showed is that the strictly valid functions are EBM functions. Okay, we didn't show it because we're not in finite dimension, but this would be the argument that would work in finite dimensions. We're in infinite dimensions, so if you look at the interiors of these things, they're empty. So even though this is correct, we prove nothing because we say the empty set is the empty set. Still, what we'll actually manage to prove is that really strictly valid functions, which are defined by this, are in K. And the way we'll do it is that by looking at closed subsets of K and showing that these things are in some closed subset of K. So they're in K. Okay? And the last thing to finish this part is that the strictly valid functions can be approximated by valid functions. Okay? So, what we said is that we started with EBM functions. We have no idea how to deal with them. We look at the bidual. It's a very nice set because it goes through operator monotone functions. So it's easy to understand what kind of functions are valid. And we show that basically, instead of talking about EBM functions, you can talk about valid functions. Okay? So now we have these new games that are very nice because we can verify what is the problem with them. Well, if I want bias epsilon, I will have an exponential number of transitions in 1 over epsilon. So you have to go an exponential number of times and check that each one of them is valid. So that's not so nice. Okay? So there's a last step that we will do, which is to get rid of the ordering. So far we are keeping the ordering of the functions or the transitions. We say you start with P0, then you go to P1, then you go to P2, and so far. Okay? So what is the last part of the thing? Is to say that, okay, forget about the ordering. I don't care about the ordering. So what do? I just define a time-independent game. What is a time-independent game? Take all the functions that are horizontal and just sum them all up and make one function out of this. This is the H. And take all the valid functions that were vertical, which is what Bob was doing, and sum them all up and come up with one function, which is this one, which is the vertical one. The good thing about these things is that if all these things were valid, then this thing is valid. Okay? So at the very end, what we really want to prove in order to say that there exists a protocol with cheating probability beta and alpha is to find only two functions, h and v, which are valid and satisfy this thing. Okay? So the only important thing about this part is to say that instead of looking at this ordered number of functions one after the other that has to do with the rounds of the protocol, what we do is that we get rid of this and we smash everything together. So that's good about finding a protocol, finding a point game, because this is much easier, but going back from this to a protocol becomes much harder. Why? Because you lost the ordering. But still you can prove that you can go back. If I give you a time-independent game with final point this, you can go to a point with transitions which is almost as good, and it has a number of rounds. Okay? And the number of rounds will be important because this will be the number of rounds of the protocol. So we need to keep track of this. Okay? Okay. So what is the problem with this? There's no problem. So now, 2 minutes, I will show you how to find this thing. Okay, for me the important thing is done. Because what I really wanted you to understand is that what are these point games? Where do they come from? And what do they mean? Okay? They're points. The points are eigenvalues of the matrices that come from the dual SDP. The weights are the projections of the honest states onto the eigenspaces with these eigenvalues. And how do you move them? You move them by some conditions that come from the operator monotone functions. Okay? Because we know how to characterize this operator monotone function. So that's all. So you have a simple way of trying to find a game. So this is what Mochon did. The game is horrendous, and we don't understand it. It's not something which is simple to describe. But in the 1 minute I have, it's going to be the following. I started with the 2 points, 0, 1, and 1, 0. The first thing I will do is that I will split this point into a large number of points. Same way I will split this point into a large number of points. Okay? The weights will be defined by this function split j. Okay? What I will have to prove at some point is that this split function is a valid function. Okay? The second thing is that I will have to move these points into 2 points. And this is the more difficult part. I will have to do a big construction here, use different points on the plane, and somehow try to move them here. I will explain in just 30 seconds about this. And then if I have these 2 points, I just raise them up, whoop, and I get to the last point. So this is nothing. So there are 2 things I need to show. This split, that it's valid for some parameters, and that this transition here is a time-independent game. So just one slide about what is this intermediate part that starts with these points and ends up with these points. Well, we cannot just take the points on the axis and move them into 2 points. We don't know how to do this. The only way how to do this is by adding new points, which we call like a catalyst points, that in their presence, things that we didn't know how to make, transitions that you didn't know how to make, now become possible. So there is this effect that if you don't know how to go from A to B, you know how to go from A plus something to B plus the same thing. So it doesn't even change. It's a real catalyst. Okay? And then you have to see how can you construct this catalyst, and the thing is little by little. And this little by little is going to take them many rounds. Okay? And this is what Mochon found. So if I define my H in this very weird way, says that you don't understand what it means, then everything is valid and it works. Okay? It's magic, but there is something that you can use. You can use a very nice lemma that says that, okay, there is a way that I know that if I put weights like that, then I know that these things are valid. The way, and it's with subpolynomials. So what the lemma says is that if I use a polynomial with certain properties in order to put weights on my points, then by default this is going to be a valid thing. Okay? So this is why we use it, and this is what he proves. If I take this omega, what is the omega is my grid, is my discretization of the plane. If I take this to go to 0, and if I take this gamma, which is the last point that I use far away to go to infinity, then I can have final point, which is k plus 1 over 2k plus 1. This is half plus k. Okay? And this is my last slide. Okay? Last slide. So, what did Mochon prove? Because this is new in the thing that we do. So what did Mochon prove is that if we take this parameter omega and gamma, one to go to 0, one to go to infinity, which means I have infinite far points and infinity close together, then I can prove a protocol with arbitrarily small bias. What we had to do is to take specific values for omega and gamma, because this is what the rounds are going to depend on, prove the same thing, do few more pages of calculations, and find out that the number of qubits is fantastic. To get bias epsilon, you need log 1 over epsilon qubits. And the number of rounds is horrendous. It's 1 over epsilon to the 1 over epsilon. That's it. I'm done. Thank you. Sorry for the 2 minutes.
1 or 2 questions. If there are any.
Okay, kind of crazy question. We've had a bunch of talks earlier about generating randomness with 2 people who don't trust their devices. And now this is a talk about generating randomness with 2 people who don't trust each other.
Yes.
So is there any hope of combining these 2 things?
I mean, one way of seeing weak coin flipping is, if you want to see it in a more quantum way, what happens is that you create an EPR pair. So you manage to create an EPR pair when I want 0 and you want 1. And somehow, at the end, we have a, not really, but you do have a 0, 1 plus 1, 0 that tells you who won. So in a very high level, which is not even clear that it's correct, you are managing to create entanglement, okay? Okay, if you want to see it more classically, you don't create a random bit, right? This is the difference between strong and weak coin flipping. It's not that the bit is random at the end. It's that I cannot bias it towards one side and you cannot bias it towards the other side. So there is this slight difference, which is not the same as strong coin flipping is impossible. So it is a big difference between getting a random bit or getting something that each one of us cannot bias, but towards one side and towards the other side.
I guess also here, each party at least needs to trust their own quantum computer, right?
Yes, so there's a question.
Oh,
Maybe can we relax
it's
that?
not a device-independent protocol.
You're only looking at the input, the possible input and output.
I mean, we don't even have a protocol, let alone a device-independent one. I mean, so, yeah.
So, okay, let's thank Iordanis again.